Hi friends, so today we start lecture 71 on our helicopter dynamics course, and today I'm going to discuss the rigid blade flap lag pitch coupled motion. So essentially we are going to bring all these three different aspects together, that's flap, lag and pitch. I'm Dr. Ranjan Ganguly, happy to see you. Now we have studied the different blade motions one by one. We have studied flap, lag and pitch. Now after some time we also studied two of these separately. So we studied flap lag, we studied pitch flap. Now we are going to study 3 degrees of motion, flap, lag and feather or pitch, and these typically would take place around 3 hinges. Now the equations of motion would change depending on the hinge sequence. Some people did research on this long time ago and they found this out. So essentially the sequence of hinges we will presume is that flap is first, that is closest to the root, then lag, and then pitch. Now some of the nonlinear terms do change if the hinge sequence is modified, so that's why it's important to keep that in mind. Now in this particular lecture, I'm going to assume that all these hinges are at the same place. The advantage is that the integration is going to be from E to R when we take the moments at the hinge. This is going to simplify the formulation without any loss of physics because we still know the integrals are there, but we do not have to carry three different numbers E1, E2, E3 or E beta, E zeta, E theta for these three hinges. Now we will also retain important nonlinear terms up to the second order, and this essentially means that when two different displacements are multiplied together and so on, we will retain those. We are going to neglect terms such as cubes, fourth orders and so on. So let's return back to our free body diagram. So this is the flap motion. Now we are considering the Flap-Lag-Torsion model. Recall that we had the centrifugal force, the inertia force, the aerodynamic force, the Coriolis force. Okay, beta is the flapping, and then we also have a spring force, and to generalize this we also would have some kind of a damping force here. So that is generally going to be present because there is some damping present in the system. There is also the usual rotation speed around the rotor hub. Now let's look at each of these forces. Recall many of these forces from our previous discussion. So we would have inertia force m r minus e beta double dot dr r minus e. There is also an inertia force component due to m xi theta double dot dr. Recall this from our pitch flap derivation. Similarly, there is a term involving centrifugal force. One comes directly from flap, which we have seen in the flap equation. Second one comes from the pitch component. There is the Coriolis force, which comes from the flap-lag problem. Then there is the usual aerodynamic force. There is the spring force. Now we have introduced beta P, which is a pre-cone. And also there is a damping force given by C beta beta dot in the usual form of damping. Now this damping force or drag force, if we call it, this C beta is going to be 2 zeta into omega into I beta. Now zeta subscript beta here is the viscous damping coefficient of the flap mode. So essentially we are assuming that all the damping effects in the flap mode are lumped into some viscous damping coefficient, and then we are considering that. Now if we take moments at the flap hinge, we get our equation here. Many of these terms are familiar to you from our previous derivation. So there's a beta double dot inertia terms, a theta double dot inertia term coming from the pitch side. There is a centrifugal force term. Wherever omega square is present, these are centrifugal force term. There is a zeta dot term with omega there. This again is a Coriolis nonlinear term, then there is a forcing term F beta, there is a spring term K beta, and at the end there is a damping term. Now again we want to simplify our equations and our life, so right now we will presume that I beta equals IB, and this is going to simplify our equation. We divide throughout by IB into omega square, and we then get the equation in flap, and that's this good looking equation here. Now let's look at each of these terms, because the main thing about these equations is the physics you can get from looking at the different terms. So the as far as inertia and spring or rotational effect terms, these are both here. Now this is a damping term which we introduced. This zeta star term is a Coriolis term, and these Ix star terms are due to the pitch flap coupling. Right hand side there is a moment coming from the fluid mechanics forces, and also there is a beta p term which is the spring force term thrown to the right hand side. Now recall our new beta square is the usual 1 plus the part due to the hinge offset and the part due to the spring, and m beta bar essentially comes from f beta, where f beta is essentially coming from the aerodynamics forces, in this case largely from lift. Also Ix star is Ix by Ib, so it can be written in this form, and of course if Xi is 0, this term becomes 0, so that is the way to get rid of the coupling between the pitch and the flap, is to put Xi equal to 0 somehow in your system. So if we want to further simplify our equations, we can consider a uniform blade, then you get this equation here, and then Ix star becomes this here, right? So we of course clearly know that nu beta is greater than 1, and we also know that it has components due to centrifugal force, that's the 1, due to the offset of the hinge, that is the E, so that increases the flap frequency, and also the spring here, that also creates some extra stiffness, so it increases the frequency. Now let's look at the lag. Now recall again from our previous derivations and so on, the lag blade here, and the lagging blade has the IF, the CF, and the AF, and the Coriolis force also comes in because of the presence of coupling between flap and lag motion here. Okay, we also have the usual spring force. We introduce a damping force here also. Now one of the interesting things here was that the centrifugal force always had this moment arm, because some E is always going to be present, and this arm was E by R minus E zeta. Okay, E is present in the lag mode because here there is no option of making E 0. If you make 0, then your lag frequency is only going to come from the stiffness, and that may be very low. So an E is of course required in the lag direction. So let's now take a look at all the different forces which act in the lag direction. So we have our usual inertia force, arm R minus E. We have the centrifugal force term, arm I just showed you, depends on E here. We have two Coriolis terms, one due to beta dot and the second due to xi. So these essentially are going to give you the Coriolis forces. Then you have the AF term, largely due to the drag. You have the spring force term, and you also have the damping force term, which is essentially a moment. So the damping force term would depend on zeta dot, and we have an equivalent viscous damping here. So zeta L is the viscous damping coefficient in the lag mode. Like I mentioned before, we essentially take the damping in the lag mode, we can lump it into this number here. Now if you have a lag mode damper, that would also somehow be included in this number if you are trying to include that in your model. Now these things look easy in equations, but it's actually quite hard to get good estimates for damping, as any person who is in dynamics will tell you, but let's leave that for a later day. So let's get back to our lag equation here. What we do then is we take the moment and then we set that equal to 0. So that's the moment at the lag hinge. So essentially E to R. Like I mentioned before, because all the E's here are being considered to be the same, there is no problem here in having E same as in flap, lag, and torsion. So again, you recall all these terms. The inertia term is here, the centrifugal term is here. This is a Coriolis term, this is a Coriolis term, this is the aerodynamic force term, this is the spring term, this is the damping term. Once again, make certain approximations and simplify our life here, and that's going to give us this equation here. So we are now looking more at the mathematical structure of the equation, so we are making some of these approximations. So nu zeta is given in this form here. Now, as I mentioned before, looking closely at nu zeta, if E was 0, only this part would be contributing to your rotating frequency, and that may be too low. That is why we need E here to basically give some stiffness to the lag system, or to give some decent frequency in the lag direction for a articulated blade. Now m zeta of course is given by this here. Remember, f zeta is coming from the aerodynamic forces. In this case it is going to be largely coming from the profile drag and the induced drag. So you're going to have the L into phi component and the D component. Let's now turn to torsion, or the pitch motion. So in the pitch motion, your pitch of the blade is theta. So now you have several forces acting here. One of the key parameters in the pitch direction is this distance xi between the feathering axis and the CG, and all the dynamics type of forces essentially act at the CG of the blade. So you have Coriolis forces, you have centrifugal forces, you have inertia forces, and so on. So let's now write down all these forces here. So we have written down here the inertia force. So this of course you are familiar with from our derivation, the mxi theta double dot dr. This second component is coming because of coupling with the pitch flap motion. So it's coming from pitch flap motion. Arm in both cases is xi. Now the IF2, which is the main component, which is present in case even xi is 0, is I theta theta double dot, and that's the uh, inertia moment which comes out here. There is a propeller moment term here which is coming out of centrifugal force. There is another centrifugal force term coming because of the centrifugal force in flap generates a moment arm here. So that's primarily coming from centrifugal force in flap. There is also a Coriolis force which is coming due to presence of zeta dot. Further continue on the torsion mode forces. The AF is there because of the aerodynamic forces which are acting in the pitch direction. There is a spring force here, and there is a drag force. The drag force here is directly proportional to theta dot, and we introduce a zeta subscript theta here to capture the damping. And as before, this zeta subscript theta term is a viscous damping coefficient in the torsion mode. Also we see that the non-rotating torsion frequency is there, and IF is the mass moment of inertia around the feathering axis. Now we take all these moments and then we sum equal to 0. So again we have taken the moments here, we sum equal to 0. Remember, all the hinges are co-located here. So here we get our usual inertia term. So both these theta double dot terms are there. So remember, there is one I0 term, there is a mxi squared term, and then there is a term due to the component of beta double dot. There is the propeller moment term, there is one more centrifugal type term here, there is a Coriolis force term here, and the aerodynamic force here. There is a spring force term here, and then there is a damping force term here, and that culminates this particular equation. So now let's take a good look at this equation and meditate on it. So we can clearly see that our old terms are here, our theta double dot is here, our theta is here. These are the bread and butter terms in the torsion mode. Now this damping of course is just something we have put in here to capture all the damping forces which act on this blade. Now sometimes there are also torsional dampers present in this system, so those may contribute damping here. So you need to lump all this into this zeta, theta. Now, like I mentioned before, that again is a non-trivial exercise. It is difficult to estimate damping, but this gives you a way to bring in damping into your model. Then there is the term involving Ix star, which involves the flap and the lag. Now, interesting thing, of course, we know this term would vanish if xi was 0. And then you have the right hand side here. The usual terms for the aerodynamic force, and then we have the non-rotating frequency here, and we have the rotating frequency here. So again, like I mentioned before, the torsion frequency tends to be somewhat large, 3 to 4 per rev. That is because the torsion stiffness component is relatively large. So 1 plus some number equal to 2, 3, 4, 5 may be there, so that when you take the root of this, it comes to 3 to 5 per rev. That's a typical torsion frequency. So all these equations, it's hard to look at them without getting severely depressed. So what we do is we write it out in matrix form. And then when we look at them in matrix form, you get a lot of physical insight into these equations. Because one of the things you get is you see why the coupling in these equations is coming. And clearly you can see here that this, let's start with the mass matrix here. Now there is a coupling term present between the pitch and the torsion, and that is created by Ix star. Now if we look at the damping matrix, there are all these diagonal terms coming directly from the viscous damping we have introduced, but there are these very interesting anti-symmetric terms. So there is a negative 2 beta, there is a 2 beta, there is a negative 2 beta Ix star, there is a 2 beta Ix star, and these are very emblematic of Coriolis forces. So these are the Coriolis terms in the damping equation. Very nice looking terms, but difficult to manage. Now we come to the stiffness part here. The stiffness part, again, we see the normal frequencies are all here. The frequencies for flap, for lag, for torsion. But again, the coupling is present due to the Ix star here in the 1 and 3 components. So again, that's coupling your flap and torsion. The right hand side aerodynamic component here, you can clearly see because of the presence of gamma that these are all coming from density of air. So if I were to set gamma to 0, which would effectively set the density of air to 0, this term would vanish and I would get the vacuum condition. So if you have any code, you want to run it in vacuum, set gamma equal to 0. And then here on this side, we have the remnant terms. We essentially have the constant terms. One of these is coming from pre-con and the other is coming from the theta con, which is a spring type term. So let's make a few points about these equations. What do we see in these equations at this point? First thing we see is that these equations are coupled. And we also see that the inertia and stiffness matrix are symmetric, but they are not diagonal. In the damping matrix, the viscous damping are the diagonal terms. The Coriolis forces are essentially anti-symmetric terms in the damping matrix, and this may be the first time you have seen such terms in your formal study, and they generally don't come in many systems except for rotating systems. So that's a particular feature of rotating system, is that these Coriolis terms are coming in and they are quite significant. So these are important nonlinear coupling terms. I have mentioned to you before also that they cannot be removed. They are not because of the deflection being large and so on. They are essentially due to the physics of the problem, and you will have to handle them using some mathematical method which you can conjure up. So that was the video about the Flap-Lag-Torsion system, and you clearly saw that all the terms derived previously were incorporated in this system, and what was new is essentially some Coriolis type of terms which came in because of the coupling. And these coupling terms are important because many times when helicopter dynamics was coming up as a discipline, there was a great lack of correlation between predictions coming out of these models and actual experimental data or flight test data. So people at first figured out that some of these important nonlinear terms were not being included. So slowly they started including more and more of these nonlinear terms till they came up with the Hodges and Dowell model, which included a plethora of nonlinear terms. And then, of course, later development took place where people tried to include all possible nonlinear terms and bypass this concept and get into more sophisticated concepts such as multibody dynamics and so on, where they could actually capture all the nonlinearities without making any approximation. But be that as it may, I would say that this kind of derivation which we have seen here and which is often presented in textbooks is a way to understand these systems physically. It's possible to see some of these terms where they are coming from. That's one of the advantages of a Newton law type of derivation. Though you have to use your thinking to come up with the terms, when you come up with these terms, you do feel very confident and very peaceful that you now understand the source of these terms and you have some handle on these terms. So that's something which your highly computational methods may not give you. So I will end this lecture here and I will see you in a video sometime soon. See you then.